So in the first example, and I realize this isn't typed the best because the formatting kind of got all squished together. But we have a function f is defined by f of x equals, and it has two parts to it. So it's 1 minus x if x is less than or equal to 1, and then it's x squared if x is greater than 1. And it says first we evaluate these three function values, f of 0, 1, and 2, and then sketch the graph. So as a review, how would I evaluate f of 0 when I have a piecewise function? You insert it, you plug it in. Why do you plug it into the top one, not the bottom? Yes, okay. So you have to look at the value you're substituting in, figure out which domain it falls into. Whatever domain it falls into, that's the expression you substituted into. So since 0 is less than or equal to 1, I substituted into 1 minus x. So I would have 1 minus 0. So f of 0 is 1. So that means if I do the same thing for f of 1, 1 is equal to itself. So again, I have to substitute it into the top expression. So I would have 1 minus 1. So f of 1 is 0. And then f of 2, 2 is greater than 1. So then I would have, or substituting into x squared, 2 squared is 4. Okay, so you might be finding function values, or rather that will come up, finding function values with piecewise functions.
Freshman students with last names beginning I through M that did not have their picture taken at registration, please report to the ACP at this time. Thank you.
Okay, and then if you were asked to sketch a graph of a piecewise function, or you were working in a problem and you aren't allowed to use your graphing calculator and you need a sketch of a piecewise function to help you out, there are different ways to go about graphing this. I'm going to show you the way that I would have taught it in Algebra 2. But if you recognize, the linear and the quadratic function and what you know about it and using the endpoint, you can graph it that way too. So the way I had showed it in Algebra 2 was to set up, if you have two separate expressions, set up two tables and just plot some points to make your graph. So one of our expressions is y equals 1 minus x. And that is if x is less than or equal to 1. And then the other one is y equals x squared if x is greater than 1. And I had showed that for both of these graphs, if you're making a table, you want to plug in the endpoint, even though in the second domain x can't equal 1, you still want to substitute that in. So I would substitute 1 in for both of them. And then I'm just going to pick one other value here. And so then in this one, I would choose another x value that's less than 1. And we had already, plugged in 0 before. This one, I would choose another x value greater than 1. And we had already substituted in 2. So we have at least 3 of the 4 values we would need here. So for this first one, I know when I substituted in 1, that y value is 0. When I substituted in 0, that y value is 1. And in the second table, when I substitute in 1, 1 squared is 1. When I substituted in 2, that was 4. So then remember with piecewise graphs as well, circles versus dots. So at this breaking point, at that x value 1, you can't have two filled in dots or points because then it would not be a function. One of them has to be a circle. So because this domain can equal 1, this function has a dot at the ordered pair 1, 0. But my bottom expression, that domain cannot equal 1, so y equals x squared will have an open and then 0, 1. And then starting at that end point of 1, 0, and I recognize that this piece is linear, I can just draw that linear piece. But you could also do that if you recognize the slope and did rise over 1. That's why I'm saying there's different ways to go about graphing these. And I could have plotted more points too if you can't quite tell what that piece of the graph will look like. The second piece I recognize is quadratic. So I'm going to plot 1, 1, but I'm going to put an open circle. And then 2, 4. And this is quadratic, so I know it would be kind of the right part of a parabola. So I don't want to draw a linear piece through it. I do want to make it appear to be as curved as I can. Oh, I need a new pen here. Okay, very quick review on sketching a graph of a piecewise function. But are there any questions on function values, sketching the graph? There is a chance for you to practice as well. Then we will be working with the absolute value function quite a bit as well. So the absolute value function is itself a piecewise defined function. And for a lot that we do with the absolute value function, we do have to think of it as a piecewise function in order to get things to work. So I just want to review, how do you define the absolute value of a number? What does absolute value mean? Distance from 0. So the absolute value of a number n is the distance n is from 0. And we know then, since absolute value is a distance, that it has to be 0 or a positive number. So the absolute value of a number cannot be negative. So I could also write this: the absolute value of n must be greater than or equal to 0. And then we have the general definition I included below. So we have the absolute value of n will equal itself as long as the value n is greater than or equal to 0. So if n is 0 or a positive number, the absolute value of that number is itself. Just to help explain this bottom one, where it says the absolute value of n is equal to the opposite of n if n is less than 0. So an example of this one is if I have the absolute value of -3, I know that's going to equal +3. -3 and +3 are opposites. So that's to help make sense of this, why it's showing the absolute value of n is equal to the opposite of itself. If n is a negative number, the absolute value of that number is its opposite because it's positive. So then the second example is just having us review the graph of the absolute value function, f of x equals absolute value of x. And what shape does an absolute value graph have? A V, yes. So you could even just sketch this right off the bat. If it's just absolute value of x, the vertex of that graph is at 0, 0. This would be the graph of the absolute value of x. So it goes through 1, 1, 2, 2, 3, 3, and then -1, 1, -2, 2. But this is why, just so you understand this, the absolute value of x, because whenever we work with the absolute value function for derivatives or integrals, we have to break it into its two pieces. It is a piecewise function. And it's defined with these definitions up here. So the absolute value of x is equal to x if x is greater than or equal to 0. and it's equal to the opposite of x if x is less than 0. So to show you this on this graph, this expression is the line y equals x. That is that piece here. That is the line y equals positive x. Starts at 0, 0, has a y-intercept of 0, a slope of positive 1. That is the right piece. The left piece is the bottom expression, because those are the x values less than 0, and that's the line y equals negative x. Y-intercept of 0, slope is negative 1. So it's decreasing if you move from left to right. Okay, so anytime, like I said, that we work with absolute value for calculus, we have to break it into its piecewise function. Any questions on that one? Okay. Am I okay to move this? Okay. I saw some people writing and I wasn't sure if they still needed to see that exactly. For sake of time right now, I want us to actually come back to example 3. So there is a problem similar to this in the practice that I have where you're looking at the graph of a piecewise function and writing the formula for it. So we will come back to that. I just want to see where we end here, but I want to make sure we review symmetry and then quickly talk about increasing, decreasing. So it says, or this part that we're getting to now is dealing with symmetry. So even functions, odd functions, or neither even nor odd. So a function does not have to be even or odd. It's not like we have functions that are even or they're all odd. They don't have to be either of them. So how these are defined, because I know, or at least I believe this comes up in pre-calc, but maybe it's at the very beginning. If a function f satisfies f of negative x, or f of the opposite of x, is equal to f of x for every number x in its domain, then f is called an even function. So as an example, to show you what this means, we have the function f of x equals x squared. I can show you that this is an even function by showing you that what I highlighted here is true. If I find f of negative x, so I'm going to substitute negative x in for x, I would then have negative x squared, but I know negative x times itself is still going to be positive x squared, which is the same as the function I started with. So therefore, f of negative x just equals the original function, thus it's even. So if you are asked to prove that a function is even or odd, or determine if a function is even or odd, this is what I need to see. I need to see algebraically that you're finding f of negative x, and if it's even, that you're showing it's equal to f of x. And you have to keep it as x. Don't substitute and say, I'm going to try negative 2, I'm going to try negative 4. Oh, it works for those two numbers, so it must be even. In order to assume it works for every single number, you have to substitute in negative x and not a specific number. And we'll go through some examples. So I also have here the graph of an even function is symmetric with respect to the y-axis. So we know if we graph y equals x squared, that is a parabola, vertex at 0, 0, but we know that that graph is mirrored over the y-axis. And every even function will have that geometric property. All right, so then for odd functions, so if f satisfies f of negative x equals the opposite of f of x for every number x in its domain, then f is called an odd function. So I have an example, f of x equals x cubed. If I were to find f of negative x, so I substitute negative x in for x, I'd have the quantity negative x cubed. And to help show this really means I'm taking negative x and then multiplying it by itself 3 times. So I still have x cubed, but a negative times a negative times a negative is now negative. So I have negative x cubed, which is the opposite of positive x cubed. So this is the opposite of my original function f of x. And thus it's odd. And the graph of an odd function is symmetric about the origin. So if you picture the graph of x cubed, I'm just going to quickly sketch it. You may remember x cubed looks like this, goes through the origin. Now x squared and x cubed, I don't want you to get in the habit of if you see a polynomial and the degree of the polynomial is even, it's automatically an even function. So because this is just x squared, yes, it's even. Just x cubed is odd. Just x to the fourth would be even. But if you see like x to the fourth plus 3x squared minus 2x plus 5, you can't assume that, well, the degree is 4, it's going to be even. You'd have to double check. So I have some examples down here where you're determining whether each of the following functions are even, odd, or neither even nor odd. So again, this is when you see this type of question, this is what I expect to see. In order to determine if it's even or odd, you just have to find f of negative x. Okay, that tells you if it's even, odd, or neither. So if I substitute negative x into x to the fifth plus x, I have negative x, that quantity to the fifth, plus negative x. So for a similar reason as for x cubed here, if I have negative x to the fifth, it'll be the opposite of x to the fifth. So that term will be negative. And then I have minus x here, or I could keep it as plus negative x. Obviously, looking at it, it's not equal to f of x. Is this expression the exact opposite? Yes, because I could factor this negative out and have x to the fifth plus x, which that was f of x.
Freshman students with last names beginning N through Z that did not have their picture taken at registration, please report to the ECP at this time. Thank you.
So because f of negative x is equal to the opposite of f of x, this is an odd function. Okay, so answer B and C, just look at those two functions, determine if they are even, odd, or neither. And we'll check those quick.
Pretty close though. But it might be rolled to the left. It's not exactly what you said. That could be either.
Yeah, so again, a reminder, functions do not have to be even or odd. They can be neither even nor odd. Not every function will be symmetric about the y-axis or different
Order of operations, sir. Oh my God.
All right, I think we're okay in terms of having answers. Just double check that you have them correct. B is neither even nor odd because it's not the exact opposite of the function and it's obviously not the same as the original function. And then C is even. Is there a question?
What? I hear you. I got it right. The third one. Oh, I got it right.
Are there any questions? All right. Last thing we'll get to here. This is really quick. So I just need your attention for a couple more minutes here. I know some of you remember this from pre-calc. Some of you asked me about it yesterday. With increasing or decreasing, looking at the graph, it's when you're moving from left to right, do the y values appear to be going up? Do they appear to be going down? This is the formal definition here of what increasing and decreasing mean. So a function is increasing on an interval I if f of x sub 1 is less than f of x sub 2, so the first y value is smaller than the second y value whenever x sub 1 is less than 2 in I. So what that is saying is as your y values are increasing, as you move to the right on the graph, when the y values increase, the function is increasing, just vice versa for decreasing. So that's the formal definition. The one thing I want to really point out to you, though, is when you are naming intervals of increase or decrease, you are naming intervals for x values, not for the y values. So intervals, unless it's a range, really the intervals that you normally list are all domain, unless it specifically asks you for a range. That would be the y values. So if we were to say where this function is increasing, I could say this is increasing on. Yep, so it starts at lowercase a and it increases until where? Till b. But we want to use the lowercase because we want to use the x values. Now, one thing I always get asked too is when you're naming intervals for increase or decrease, do you use brackets or do you use parentheses? Different like textbooks or different answer keys for things will show different or will show both brackets and parentheses. And from what I understand, even hearing from people that grade AP tests, is it doesn't matter which one you use. They would accept either one. So I guess later on in there, I know I just put brackets here. Normally you'll see me put parentheses, but it doesn't matter is what I've been told. And then this does increase again from C to D. So I would say increasing on the interval from A to B, union C to D. And then decreasing, obviously, from B to C. Okay, so just make sure you're naming the X intervals, not the Y.